Hey everyone, before we talk about absorption in small intestine, I want to review really some things we've learned even back in 141 that are really critical here. So remember in the digestive system is like a big tube going through our body. So something can be in our digestive system without really being in our body because we haven't absorbed it yet. Does that make sense? And it's a great thing because it allows us to put things into our body without them being absorbed. Our body is able to be really selective. All right, so how is this going to work? What do we need to know here? What I want you guys to know going into absorption is simple columnar epithelium is what is lining the lumen of the small intestine. Remember, we have that brush border, the microvilli. We have tight junctions in between the cells. And what are tight junctions? Are they super, super, super strong, like what we saw in cardiac? No, they're not super strong, but they're tight. Tight in what kind of way? Tight in Ziploc bag kind of way. They seal. So they keep things from going between the cells. That means that things have to go through the cell. And so transcellular transport. Going between would be paracellular. So this is transcellular transport is what we're going to be doing in these situations here. Now, I want to also review hydrophilic and hydrophobic. If something's hydrophobic, can it pass through the cell membrane? It can, right? But can it travel dissolved in the blood? It cannot. So what's going to be hydrophobic that we're going to talk about? How about lipids, right? All right, hydrophilic. What are properties of hydrophilic? Can they pass through the membrane? They cannot, right? They're hydrophilic. Hydrophobic can get through the cell membrane. Hydrophilic cannot, but hydrophilic can travel dissolved in the blood. So what is this, these dots here? Would those be hydrophilic or hydrophobic? They're getting through the membrane, but they're also traveling in the blood. Oh, but look, they're getting through the membrane because they have a transport protein. Are you able to see? I made a blue protein there. And then down here, they have a transport protein to help them get out. Something else I want you to know. Remember hydrolysis back from chapter 2? And a water molecule is added in, and let's say there's two monomers put together. A water molecule is added in, and they're split. So hydrolysis. You add water, hydro, and you split it apart, lysis. So let's do that. Hydrolysis, water, split. And enzymatic, what does that mean? We're using enzymes here to split these dimers into monomers. And why is an enzyme? It is actually something that would happen naturally, but when you use an enzyme, it happens faster. It wouldn't happen naturally at the speed we need it to, and we wouldn't be able to absorb any nutrients. Okay, does this make sense? And I want you to remember that we have blood vessels, and remember we've talked about lacteals. We have lymph capillaries, lacteals, and with their mini valves. Something to keep in mind. We'll be talking about both of those. One more thing that you want to remember, and I'm sure you do remember, is the sodium-potassium pump. Sodium-potassium pump. That's going to, remember in muscle cells it establishes a gradient. We're going to do the same thing here. We're going to end up having a sodium-potassium pump at each cell that's going to establish a gradient. We're then going to use that gradient to pull things in. All right. Do you feel ready to move on to absorption? I'm going to make a different video for each monomer.